Okay, so now that we've seen the definition of a group and tried to explain a bit more concretely what it means, let's see some examples. So let me start out with some trivial examples and then do two non-trivial examples, as I mentioned before. So the trivial examples are that all of the number systems that you are used to are examples of groups under addition. Okay, so Z, the integers, Q, the rational numbers, R, the real numbers, and C, the complex numbers. These are all groups under addition. What does it mean under addition? It means that this multiplication map G dot H in this case is just the sum of G and H. And in all of these cases, the identity is just the zero, the number 0. Okay, and what is the inverse? The inverse of G is just minus G for an element G and any one of these Z, Q, R, or C. Okay? Now, there's something less interesting about these examples than about the examples that I'm going to do next, which is that these are all abelian groups. What is an abelian group? So, definition, a group G is abelian if G times H is equal to H times G for all G and H in G. So while every group is associative, that is, the order of the parentheses doesn't matter, a group is not necessarily abelian or commutative, meaning you cannot just move around the elements across one another. When you can do that, gets a special name called abelian. So let's see now an example of a non-abelian group. Okay, so you've all had linear algebra before. So example of a non-abelian group from linear algebra. So for this, we need the notion of a field. So, well, let's maybe take, let F be a field. If you don't know what this is, Q, R, and C are three examples of fields. So if you haven't seen this in linear algebra, just take, for example, F equals Q, R, or C. Okay, then GLN of F, this is by definition the set of A n by n matrices with coefficients in F such that A is invertible. Okay, and from linear algebra, you remember that A is invertible is equivalent to saying what? It's equivalent to saying that the determinant of A is non-zero. And now what I claim is that GLN of F, so in particular GLN of Q, GLN of R, GLN of C, these are non-abelian groups. GLN of F is a non-abelian group once n is at least 2. Okay? Okay, so we just defined the group GLN of F. Let's check that it is in fact a group. So we need to get practice checking the group axioms. So what do we have to do? Check that GLN of F is a group. So we should check that it's closed under multiplication first. What does this mean? I take A and B in GLN of F. I need to show that the matrix product A times B is again in GLN of F. Okay, now there are several ways to see this. One way is, remember we said so a priori what we're worried about is that this product, it's obviously again an n by n matrix, but we need to check that it's invertible. Okay? One way to do that, we've said one characterization for a matrix to be invertible is that its determinant is non-zero. So we can apply that to the product here. We can look at the determinant of A times B. And from linear algebra, you know that the determinant is multiplicative. So the determinant of A times B is the determinant of A times the determinant of B. And now our assumption that A and B are in GLN of F implies that the determinant of A is non-zero. Our assumption that B is in GLN of F implies that the determinant of B is non-zero. These two elements are non-zero elements in the field F, so when I multiply them, it's also non-zero. And that implies that A times B is again in GLN of F, which is what we wanted. Okay? Let me come back to another way to see this when we check the rest of the axioms. For now, let's move on to checking the identity. So we need an identity element. What is that going to be? Well, it's going to be just the identity matrix. Which I often write I sub n. So this is just the matrix that has ones along the diagonal and zeros everywhere else. All right, and then you know that the identity matrix times any matrix, in fact invertible or not, gives you back that matrix. So this is a good identity for the group. Okay, what else? Inverses. So, well, we have, if A is invertible, we know that it has an inverse matrix A. And A inverse is again invertible. And we know that A inverse times A is A times A inverse is the identity. Finally, we have to check associativity. Okay? Now, there are a few things we can say here. One is we can say from linear algebra, we know that multiplication of matrices is associative. But let's briefly recall what is a nice way of seeing that about matrix multiplication. Namely, that matrix multiplication corresponds to composition of linear transformations. So remember that if I have A an n by n matrix, I can think of A as a linear transformation from the vector space f to the n of vectors of length n to itself. And then what does it mean to say that A is invertible? A invertible if and only if this linear transformation is invertible as a linear transformation. That is, if and only if this map from f to the n to f to the n is an isomorphism. All right. Now, what is then associativity? Then associativity of matrix multiplication is just the associativity of composition of functions when we think in terms of linear transformations. So we know that if we have three functions, f, g, and h, it doesn't really matter what their domain or range is, so long as we can compose them. We know that f composed with g composed with h is f composed with g, all of that composed with h. Applying that to the linear transformations associated to three matrices, we see that matrix multiplication is associative. So all in all, we have checked that GLN of f is a group. And I said to check that it's closed under multiplication, I checked this first with a determinant. We can also use this point of view of the linear transformations. If I have A and B are invertible, that means I have two isomorphisms, A and B, from f to the n to f to the n, then also the composition of those two linear transformations will be an isomorphism. You can check that. So you can check that, again, they will be injective and surjective. All right. OK, so we've checked that GLN of f is a group. Now let's quickly check that it's also non-abelian when n is at least 2. So let's do the case that, for simplicity, let's do the case that n is equal to 2. So GL2 of f is not abelian. So we need to find two 2 by 2 matrices that do not commute with each other. So we could take, for example, diagonal matrix A1, A2, and I multiply it by this upper triangular matrix 1n, 0, 1. So I multiply them in this direction first. So what do I get? So if I multiply for the first column here, It's just the first column of this matrix because I have the standard basis vector here. So this is A1, 0. And then what do I get here? I have A1n plus 0 times 1 is A1n. And then I have 0 times n plus A2 times 1. So I get this matrix. Now let's multiply in the other direction and see what happens. So I put first this upper triangular matrix with ones along the diagonal. And then I put this diagonal matrix. By the way, to make sure that this one is invertible, we should assume that A1 and A2 are both not equal to 0. All right, now let's multiply this way. So we have A1 here. Remember, the product of two upper triangular matrices is always upper triangular. So I know there's going to be a 0 there. And then A2. And then what happens here? I have 1 times 0 plus n times A2. I get n times A2. And now notice that these two are different because here I have n times A1, and there I have n times A2. If you pick, more generally, if you try this at home and you pick two 2 by 2 or larger 3 by 3 matrices at random, most likely they will not commute. There's a special reason that I've chosen these particular ones, which we might get to later on in the course.